Welcome back. This is week 6 of inverse methods in heat transfer. We are doing a review of basic probability theory in this week. In this video, I'll primarily be talking about two ideas or two things that we extract from a probability distribution. These are called expectation and variance, and both these arise out of the probability distribution function, or of course the probability mass function in case it is a continuous a discrete variable. But our primary idea is to extract these two main things. Now you would have seen expectation as the idea of mean in the usual statistics class, and variance of course and standard deviation etc. are related to these ideas only. There is a slight twist to these and how these become important once we start looking at continuous distributions as well as discrete distributions when we look at the entire distribution. So I'll go over that. These are very, very central ideas. Again, we will use them very regularly within the next week within inverse methods. It will be seen in the next week that it's the expectation which we were predicting in the usual function approach. We will talk about this more, this kind of point prediction when we come to the next week. So what we are doing right now directly feeds into what we will be doing next week, which will be applying probability techniques directly to inverse methods. So let's look at a couple of ideas. The first idea is that of independence. You would have seen this again earlier within school, within college, etc. So two random variables x and y are said to be statistically independent if and only if. Okay, so this is the definition of independence. P of x comma y is P of x multiplied by P of y. Now you have to be really, really careful when you say this. You have to be careful because remember, x can take a range of values. Okay, so if it's continuous, all possible ranges of x, and if y is continuous, all possible ranges of y, or if let's say x is throwing a dice and y is toss of a coin, then x has a sample space of 6, y has a sample space of 2. What should be true is P of x equal to x, y equal to y should be this for every possible value. Okay, for all values of x and all values of small y. For example, if I ask the question, what is the probability that the dice threw a 6 and the coin was a heads? You will say this is the same as the dice being 6 multiplied by the probability of the coin being a heads. So this, of course, is 1 by 6 into 1 by 2. But this is not enough to establish that the throwing of a dice and the tossing of a coin are independent. What you have to do is this should be true for every possible value of x and every possible value of y. Okay, so if x is 5 and y is a heads, etc., etc., it should be true. Now, an example of independent variable are the things that I have shown. Physically, we realize that the throwing of a dice and the tossing of a coin are independent. Non-independent characteristics are things like height and weight. Okay, it doesn't mean that everybody who's taller will weigh heavier, but there is some correlation. And we'll come to this a little bit later within this video, what this correlation means and how we measure it. Okay. Now, independence, it's more obviously seen, is the equivalent of saying P of y given x is the same as Py, or that P of x given y is Px. For example, what is the probability that I will throw a dice given that I tossed the coin and got a heads? Like, why should it depend at all on the tossing of a coin? It doesn't. So P of x given y is the same as P of x. And similarly, P of y given x is the same as P of y. X has no effect whatsoever on it. So now if we apply the product rule here, we say that P of x comma y, P of x and y occurring is the same as P of y given x multiplied by P of x, which is the product rule. Now, we already know of P of y given x if it is independent. is P of Y. So P of X comma P of Y. Okay. So we can derive this product rule from here, or we can derive this rule P of X comma Y equal to P of X into P of Y from here as well. So both of these are interchangeable. Now, an important characteristic is this. IID, okay, often written in small letters, IID. You will see this multiple times within, again, especially within inverse methods literature. This means independent and identically distributed. So what it means is two or more random variables which are independent. Of course, the first I is that, and have the same PDF is identically distributed. Again, let's take our slab example. Now, if I say that the measurements at 1 and 3 are IID, what this means is that T1 and T3 are independent random variables. That is, if I find out the probability of T1 occurring and T3 occurring together, it will be the product of the individual probabilities. Now, this might or might not be true in a slab, but generally, often in inverse methods, we assume this to be true. And we will use this in the next week. But why we assume this, why it could not be true is, of course, like the temperature here, let's say it affects the temperature there, then maybe the random variables might not be actually independent of each other. So if one affects the other, they might not be independent. Second part is identically distributed. What that means is that if both of them have a probability distribution function, they look the same. Now, this does not mean that both of them have exactly the same values at each time. Obviously, that would mean they are not independent. But what it means is when I draw the probability distribution function, so they are identically distributed would mean that T1, if it lies between 15 and 20 and has a certain shape, then T2 also will lie between 15 and 20 and have the same shape. So the probability of getting 17.5 here and probability of getting 17.5 here would be the same. A simple example in discrete cases would be, let's say you have two coins, you have two friends, both of them are tossing a coin. Okay. So both these events are IID events. You toss a coin and your friend tosses a coin, and both of them are independent. Your toss has nothing to do with the friend's toss. And similarly, both of you will get approximately heads as well as tails with the same probability. Okay, provided the coins are actually both fair coins. Okay, so that is the meaning of an IID variables. So you could have this for 2 variables, 3 variables, n number of variables. All of these random variables which are independent and have the same PDF are called IID variables. Now we come to the important idea of expectation. The expectation is simply an extension of the idea of statistical idea of mean, except mean generally applies to finite samples, but effectively expectation is what you expect in the infinite limit or the very, very large limit. Okay. So to give you an example, let's say you have 2 people, okay, within a room, and one of them is 4 feet high and another is 6 feet high, then the mean is simply 5 feet. But if you ask what is the expected height of a human being within India, let us say, so that would be expectation. It's effectively taking the mean of every person in India. We usually cannot calculate expectation with simple statistics. We can calculate an approximation of that expectation, whereas mean is for a finite sample. Again, to give you an example, let's say an election takes place and you wish to find out what is the expected outcome. So you would have seen these polls. They take polls, exit polls from various elections, and based on the mean is what they calculate, but expectation is what they estimate. Expectation is the expected outcome of this election is 53% vote for XYZ party and 40% vote for PQR party, etc. So expectation is what would happen in case everything was taken to the full sample. Whereas mean is what happens for an actual small sample. Okay, so we call it infinite limit versus finite limit is what the mean is. Okay, so recall that random variables by definition result in different outcomes, and the variation in these random variables, basically what happens is captured completely. In fact, I should say, as far as probability is concerned, complete information about the randomness in this variable, okay, is captured by the distribution. Okay. Now, expectation is simply what is called a summary statistic. Okay, so if I ask, what is the temperature in Chennai at this point of time, I would say, oh, the average temperature is 17 degrees centigrade. Actually, throughout the day, it might have never really hit 17. Okay, it could have actually jumped a couple of degrees here, there, up and down at your actual measurement. But what it is a sample, or it's a summary of the sort of temperature variation you saw through the day. Okay, so it's what is known as a summary statistic. Okay, so 20% of the time you could have been at a certain place, 40% of the time you could have been somewhere else. So that summary is an expectation. That's the mean. The variance tells you how much fluctuation is there, as we will see later on. Okay, so some overall properties. So these two are not complete descriptions. Expectation and variance. What is a complete description? Of course, is the distribution. You say how much each variable is likely to take. Now, that is often difficult to capture. You might more easily capture at least what is called the first moment, the expectation, and the second moment, which is variance. Then you have other things called skewness, which is the third moment, and kurtosis. Okay, we will not cover these. But anyway, I have talked about moments, etc. We will see what they mean shortly. Now, what is the expectation? The expectation gives you the mean, average, expected value of a random variable given the distribution. So this is important. If you knew the full distribution, you could calculate the expectation. But as you will see, well, I will not discuss this in too much detail. That would belong to a full course in statistics. You will not have the full distribution. You will have only some samples of the distribution. So samples, like I said, give mean, and the distribution gives the expectation. So you could ask questions like, what is the expected return on a certain investment in the market? Okay, I give this, what are the expected returns? What are the expected returns of this mutual fund? Okay, what is the expected rainfall during the coming monsoon? What is the expected heat flux in this configuration? Okay, so similarly, you could ask that question. So typically, when we asked for heat flux before in the last 4 weeks, we were actually asking for the expected heat flux. As you will see, the values that we got out of linear regression were actually the expected values of the heat flux. Obviously, we know that given the problem is ill-defined, it's ill-posed, there will actually be a variation. Heat flux could vary with various probabilities. What we got was the expected value of the heat flux, as I will show you in the next week. Okay. So what is the definition? I'm just going to talk a little bit about the notation, and then we will come to the definition. The expectation of a function is simply the average value of that function when x is drawn from P. Okay. So here is the notation. X tilde P means x is drawn from the probability distribution P. What does is drawn from? You can just assume it's a box. Okay, so I say the orange is drawn from the box blue, and therefore the probability of x being drawn from this distribution of 6 oranges and 2 apples is 6/8. That will seem like a very complex notation, but that is usually the way it is done. I'm going to try to skip this notation because it's more important when we do very formal probability. And I'll just lead you through it, but you might see this in books. So it's my duty to actually tell you what it means. If P is clear where you are drawing from, okay, which probability distribution you are drawing from. If it is clear, then we simply say expectation over X of this function f of X. If X is also clear, then we simply say E of f of X, or we simply say E of F. Okay. Like I said, a simple calculation of expectation is simply the mean. Okay, so we'll see what that means. So how do we define expectation mathematically? Mathematically, it is very simple. I'll show you a few examples here when it becomes clear. But the formula is probability of X multiplied by f of X. The simplest expectation is expectation of some variable X is sigma xi probability of xi summation over I. For example, if I toss heads, which is 0, and tails, which is 1, and each of these have probability half, this is the probability mass function, then expectation of getting heads, or the net expected value of this variable X, of this random variable X, is 0 times half plus 1 times half, which is 1 by 2. Or there are two people, one has height, or one has 4 sweets, another person has 6 sweets. I randomly pick a person with probability half each. What is the expected number of sweets that I will get? 4 into half plus 6 into half, which is 5. Now, all these are trivial. You can see that this becomes exactly the mean. Okay. For example, if something repeats multiple times, that's basically why this counts as X times P of Xi. In the continuous case, P of X, of course, is replaced by P of X dx. As you remember, P of X is capital P of X per unit length. So in the continuous case, expectation becomes integral of P of X, f of X dx, where f of X is the probability density function. Oh, sorry. P of X is the probability density function. And f of X is the function you are approximating. More specifically, if you want expectation of X, just X, not a function of X. Function of X, for example, would be X square. So suppose one person has $4, another person has $6, and I want expectation of the amount square, dollar square, then it will be 4 square times half plus 6 square times half. So this would be the expectation of X square, where f of X is X square. But simplest expectation is expectation of X itself. So expectation of X is integral of X, P of X dx over all possible ranges of X. So if we have multiple variables, and X, like in the temperature case, is multiple variables. It's not just temperature at one point, but it's temperature at 6 points. Then we just take expectation over all those 6 variables. Now you can do this in multiple ways. Similarly, X could have multiple components. For example, in a slab at a point, this could depend on X1 and X2. That is another example. So you can look at it as multiple variables, or multiple independent variables, or multiple dependent variables. In all these cases, you can actually take expectations along independent directions. So you simply list it. You just list these number of expectations separately. Expectation along X, expectation along Y. So you do partial independence there. So here is a simple example. This is the example that I did a little bit earlier. I'm just doing it a little bit more formally here. A good way to think about expectation is as a value. So notice this word value. So I can't say if you get heads or tails, what is expected? You can't say head and a half. But we can think of it as a betting game. So a betting game would be something like this. You get 1 rupee if you toss a heads, and you get 0 if you toss a tail. Then if you do a lot of tosses, what is the average amount of earning you will get per toss? That would be the expected value of a single coin toss for a fair coin. So now notice, I am going to do this formally. The random variable we are choosing is X. The probability P from which we are drawing is a uniform distribution. It looks like this. Probability that X equal to 0 is half. This is the distribution, remember. Probability X equal to 1 is also half. So when I say X is drawn from P, X is drawn from here. So now this X is randomly drawn. When it is randomly drawn, it either becomes 0 or it becomes 1. That's the mathematical way of thinking about it. And as we have our formula for expectation as small x, P of x, this is 0 multiplied by the probability of 0, which is half, plus 1 multiplied by the probability of 1, which is half. So the next expected value is half. Now, similarly, you can ask another question. If you have a fair dice, what is the expected value of a fair dice throw? Again, you will never get this value exactly. But if I were to earn 1 rupee for throwing 1, 2 rupees for throwing 2, etc., this is the expected value of earning with 1 throw. Okay. So that's the mean earning per throw. If you average over a large number of throws, that's one way of thinking about it. P is again a uniform distribution. So notice this word. Uniform distribution means each one of these has the same probability, which obviously has to be 1 over 6. So we now write expected value of X drawn from this P is sigma of X, P of X, which is 1 times 1 by 6 plus 2 times 1 by 6, which is basically 1 plus 2 plus 3 plus 4 plus 5 plus 6, 21 divided by 6, which is 3.5. So these are some simple examples of expectation. So let's make the example slightly more complicated and have two. It's like we can now look at the joint distribution now and see how that affects expectation. Now let's take the case where 2 dice are thrown together. And once again, the random variable is X, and X has this sample space. Okay, so X is the sample space which goes from 2 to 12. And what is X? X is the sum of the 2 dice. There is no 1 there because it only will vary between 2 and 12. Okay. Now the random variable X has several possibilities. You get 2 only if you get 1 and 1. And the possibility of that, of course, is 1 by 6 multiplied by 1 by 6, which is 1/36. Similarly, 12 also has a probability of 1 by 36. So you can now draw sort of a probability table of value of X versus P of X. So 2, the probability is 1 by 36. 3 can occur as 1, 2 or 2, 1. So the probability now becomes 1 by 36 for this and 1 by 36 for this, basically 2 by 36. Okay. 4 can occur in 3 ways, 1, 3, 3, 1, and 2, 2. So on and so forth. You can now draw a table. So 2, 3, 4, 5 up until 12, which is what I have written here as a summary of the distribution for P. So the P distribution is 2 is 1 by 36, 12 is 1 by 36. You can see 7 is 6 by 36. And similarly, you have this. If you draw it, it will look like this. 2, 3, 4, 5, 6, and then 7, and then 8, 9, 10, 11, and 12. So you will see some such rough shape. Of course, it's not continuous. It's a discrete probability mass function, and that's the distribution. Now, once again, if I ask what is the expectation of X drawn from P, which P is this distribution, then it is sigma of X, P of X. So 2 times 1 by 36 plus 3 times 2 by 36 up until 12 times 1 by 36. And in some sense, not surprisingly, you get 7, which is actually the exact middle of this entire value. Now, as it turns out, there was an easier way of calculating this. Okay, you might see that there is something suspicious here. For one dice, it was 3.5. And for 2 die, the sum is actually 7, which also happens to be the sum of their individual distributions. Now, if it is 3, is it actually 10.5, or do we have to make this gigantic table with giant probabilities again? Turns out we don't, because there is something called the linearity of expectation, which is an extremely useful property to utilize. So as it turns out, there is an important property of the expectation of random variables, which is that the expectation operator is linear. Okay. What does linear mean? Linear means this. If you have a function f of x, okay, and it is, so for example, let's say f of x is alpha x square plus beta x. Okay. Then if I want to find out expectation of f of x, this will be alpha times expectation of x square plus beta times expectation of x. Okay. Another way of writing it is the way I have written it here in the most general case. If we have expectation of g of x multiplied by alpha, alpha is a scalar, it's just a multiplying thing, this is a function, plus beta times expectation of h. This turns out to be very, very useful. Okay, so for example, I have x as a function of 2 random variables, d1 and d2. Okay, remember, d1 was the outcome of the first dice, d2 is the outcome of the second dice, and x is the sum of these two. Then using my expectation property, I can simply say expectation of d1 plus expectation of d2 will be the expected value of the net sum of the die, okay, which is very powerful. So similarly, if you have x is x1 plus x2 up till xn, then expectation of x is the expectation of x1 plus expectation of x2 up till expectation of xn. Okay. Now, this is much simpler to use this because you don't need to find out the distribution of x. So remember, when we were doing it together, we actually had to find out how many times does 2 occur, how many times does 3 occur, you know, how many times 7 will occur, 3, 4, 4, 3, 1, 6, 6. You have to do none of those counts. All you need to do is when one dice came, my expectation was 3.5 and 2 dice comes, regardless of how these things arrange themselves, it's still going to be 7. Okay, so that's a remarkable property. Here is a quick proof of this. This will look like it's a complicated proof, but it is not. Okay, so we just go directly with the definition. So the definition was this: if I have a function f, then expectation was defined as f of x multiplied by p of x dx, where p of x is the PDF of x. Okay. Now we already know f of x is alpha gx plus beta hx. So this is f of x. So I have just substituted that here. Open these up. Because integral is linear in alpha, you can take this alpha out. Alpha g of x px dx plus beta h of x px dx. And this, of course, is expectation of g, because this always is PDF of x, not PDF of g of x. Similarly, this is beta expectation of h. You can prove this case discretely also. I mean, I just showed it for a continuous case because integrals are a little bit more easy to look at rather than summations, in my opinion at least. So, but this can be proved similarly. You can try this as a very simple exercise. So what we have seen so far is expectation. I had intended to show variance also in the same video but this video has already gotten a little bit longer. So I will show you variance, what variance is starting in the next video. So I'll see you in the next video. Thank you.